So to begin with on this problem, I think we're on this problem. Is that right? I think I did the previous page. Is that correct? Okay. All right. So let me go through and let's look at this. Now, the first thing is, how do you know this is a power series? You want to make sure you understand that. Well, you have an x. Number one, you have a variable x. That's what's different about this, is you now have a variable, and then it's to a power. So x is being raised to a power, so it's a power series, okay? It is going to alternate. What makes it alternate? That thing, not that thing. I'll press that button, I always do the wrong thing. So that's what makes that alternating series then, okay? So what we're going to go ahead and begin to do with this now is we're going to find the radius of convergence and everything here. So to begin with, what we generally want to do on this is we want to show this. This is ultimately what we're looking at. We want to show that the limit as k goes to infinity of the absolute value, this is like a ratio, a sub k plus 1 over a sub k, like you're doing a ratio test, is less than 1. Now we're doing an absolute value because we're looking at absolute convergence, and that's defined to be less than 1. And then we end up at the end of the problem finding a interval, so we end up solving an absolute value inequality. So that's kind of how you can remember to do that correctly then. Okay, now what I'm going to do on this is, this one we're going to do a ratio test on, okay? So when we set up and start working with the ratio test, we want to go ahead and just get this thing kind of put together like this. So let's go ahead and bring down and write, we have the limit, k goes to infinity. Now when you do a ratio test, okay, what are you doing? The first thing is you're taking the series and you're making it go to the next term, right? So how do you make it go to the next term? K becomes k plus 1, right? Okay, that's pretty logical. Okay, so let's go ahead and write that down. So that's negative 1 to the k plus 1. Be real careful when you do this now. Times k plus 1 times x minus 4 raised to the k plus 1 all over 2 to the k plus 1. Okay, now that takes care of that part. That's a sub k plus 1. That's the next term in the series. Okay? Now, you divide by the original. Now, when you divide by a sub k, what are you really doing? You're multiplying by reciprocal, right? So if you're doing a ratio test, just go ahead and write that first step that way, okay? So I'm going to put the next term like this. This is just the reciprocal. So that's going to be 2 to the k power over negative 1 to the k times x minus 4 to the k power like that. And that's all in an absolute value like that. And then what we need to do is we need to go through and do a little bit of simplifying on this before we do this limit and then solve this inequality. Okay? Some of this you'll be able to do in your head. I'm going to try to kind of carefully write down what I have here as I'm working this out. So I'm going to just try to put this all in one big fraction, and I'm going to break some stuff up a little bit here. So for instance, if you look at this piece right here, right there, I'm going to break that up into 2 to the k times 2 to the 1. Okay, I'm just going to break everything up. Then over here I've got negative 1 to the k. I'm going to leave that alone for now. Then I'm going to leave the k alone. And then I'm going to leave alone the x minus 4 to the k. Because what I'm doing is I'm trying to look for things that cancel out. Okay? I'm going to, up on the top, I'm going to do kind of the same thing. When I do this thing, negative 1 to the k plus 1, I'm going to write that as negative 1 to the k times negative 1 to the 1. I'm going to bring down the k plus 1 like that, leave that alone. The x minus 4 to the k plus 1, what would be a good way to break that up, by the way? X minus 4 to the k times x minus 4 to the 1. Okay, so I'm just splitting apart the exponents. Okay, because you know you add exponents when you multiply anyway. All right, so I'm just kind of splitting this up. I think in general it's kind of good to start learning it this way, and then as you get a little more experience, you can start going through and doing some of the cancellation in your head. Just be careful about that when you do that then. Okay, so let's see kind of what we have going away here? So one thing I see is I've got a x minus 4 to the k dividing out, and I have a 2 to the k dividing out like that, okay? Now the other thing that I look at on this, and you can look at this like this, you can do this in your head. Remember, we're doing an absolute value, okay? So if you do an absolute value of, if you did an absolute value of negative 1 to the k, does that make sense to everybody that that would just be 1? Okay, because anytime you take negative 1 to any power, it's either going to be negative 1 or 1, right? So if you're doing an absolute value, that's 1. So actually, this thing right here is just going to become 1. That thing already is 1 because the absolute value of negative 1 is 1. Same thing here. Now, you could also cancel those things out. I didn't even see that. But this thing right here is going to be 1. So what we're left with now, let's go ahead and write what we're left with. We have a limit as k goes to infinity, and we're going to have in the numerator, you can just disregard that now because that's 1, because it's an absolute value. So it looks like we have k plus 1 times x minus 4 to the first. Okay, then in the denominator, it looks like I have 2k, and I believe that's it. Okay, so I've done all the simplification I can. All right, let's pause there and tell me if you have anything that you don't understand so far. Now, I set up the ratio test, which we've talked about that. Most of that is algebraic manipulation and simplification. All right. Now, the next thing is real important on this. When we do this limit, see, the limit is dealing with k. So see, x minus 4 is a different variable, so you treat that as a constant. This is real important when you're working with power series like this. That just comes out. Just bring it out. It's a constant. Okay? You're going to be only interested in the limit of those k terms like that. So I'm going to have you write that as x minus 4 multiplied by the limit as k goes to infinity of, and looks like we're going to be left with k plus 1 over 2k like that then. Okay? So that's what we're going to end up having then, is going to do that limit right there. Okay? Now, you could also do this. I didn't even think about this. It doesn't really matter, but if you want to take that 2 out, you could have also taken that 2 out. So I probably should have done that, although it doesn't really matter. So I'm going to go ahead and just take this and put that out like that then. Okay? Now I'm in good shape. Okay? So I've got everything the way I want. And this is what you're typically going to do with a problem like this. The x stuff comes out of the limit. Now your job, and I'm hoping by now you can just do this limit like in 2 seconds. What's that limit? 1, right? How come? Okay, that's really that. Now it's an infinity over infinity form. You could do L'Hopital's rule, and if you did, you'd just get 1 over 1. Or the degree of top and bottom are the same, so the coefficients are 1 over 1. So what we have then is, therefore, we're going to end up with x minus 4 over 2 times 1, like that, okay? And technically, all this stuff should be an absolute value. I'm being a little sloppy about that. So that needs to really, when you take all that out, be an absolute value like that, okay? All right, so I've got this result. So that means I just have absolute value x minus 4 over 2. Okay, now what we're trying to do is we're trying to find an interval where this converges. Okay, now you need to make sense of this now, because you need to try to understand this. See, since it's a power series, we have no idea what x is. X could be any number. It could be negatives, positives, decimals, any real number. And it turns out that on a lot of these problems, only a certain range of x's will cause the series to converge. And then some range of x's will not work. So what our job is to determine what values of x would make this infinite series converge. Does that make sense? Okay, that's what, because it's x. We don't know what x is, all right? So what we do now is we do this. We were trying to show that this thing's less than 1. So this thing is going to converge by the ratio test. And see, if you look at the ratio test, if you can see on your on this thing right here, the condition for convergence really is the limit that we just did has to be less than 1. Okay? Now we're doing an absolute value because we're going to end up coming up with an interval on that. So what we do now is we do this. So we just do x minus 4 over 2 is less than 1 and then we end up solving that inequality. All right? Now that inequality like that, you usually learn how to do that in college algebra, Math 55, intermediate algebra. You go like this. You just say x minus 4 over 2 falls between 1 and negative 1. And then you solve that inequality. You try to get x by itself in the middle. That's the general idea. Okay? So the way you're going to do this, you probably want to get rid of the 2. So the way I'm going to do this is multiply everything by 2, like that. Okay, and then when I get that, that's going to give me negative 2 less than x minus 4 less than 2. Then you can add 4 to each piece if you want to. You can do that in your head if you want to. So that's going to end up giving me 2 less than x less than 6. Okay, so what we have right now is we have an interval of convergence. Now, we're not quite done with it, but what we're concluding is if x is between 2 and 6, in that original series, if x is between 2 and 6, then that's going to converge. When you're outside of 2 and 6, like if you're bigger than 6, smaller than 2, that series is going to diverge. We're not done, but does that make sense, at least what we're trying to accomplish? Okay, all right? So we're not done. What you need to do is you now need to test the endpoints of this interval. Okay, like this. Now this is something you'll be seeing in next week's test. Okay, I mean this is kind of a classic problem. Power series, find the interval and radius of convergence. This is something you definitely need to know how to do. Okay, so I'm going to do a couple of more illustrations of this before we finish this up. Okay, what we do is we go ahead and let x equals 2, and then we let x equals 6. Those are the endpoints of that interval. Now what I'm going to do on this then is I'm going to go all the way back to the original problem. The original problem is this power series right here. Now we're going to test those endpoints and see if we get convergence or divergence. Okay, so what you want to do now is just go to your series, and we're looking at the series negative 1 to the k times k. Now replace x with 2. Okay, so you're going to say 2 minus 4 to the k all over 2 to the k. And then we'll work that out in just a minute. And then we're going to do the same thing with 6. So let's just go ahead and get both of these set up. So we're doing series, negative 1 goes to k, negative 1 to the k power times k. Now it's 6 minus 4 to the k all over 2 to the k. Okay, so you want to get everything set up. And now what you do is you kind of use the knowledge that you have obtained on series to see if these things converge or diverge. Okay, they usually turn out to be things that you would recognize, like maybe an alternating harmonic series or a harmonic series or a geometric series, something like that. So what I'm going to do is when we do this, let's clean this up a little bit. We'll have series negative 1 to k to the k power times k, and this is going to be times negative 2 to the k over 2 to the k like that. Okay, now these things right here do not cancel out, but you can do this. You can write this as series negative 1 to the k times k, and you could write that whole thing as negative 2 over 2 to the k. That's just a standard algebraic property of exponents. If you have a numerator, denominator, both to that same power, then you can just put the whole thing over, negative 2 over 2 to the k. Well, that's going to be negative 1. So I'm going to write one more step, and then we'll kind of see where this leads us then. So we have series negative 1 to the k times negative 1 to the k. All right, everybody see how the algebra is going on that? Right, because that's mostly what this problem is algebra when you get right down to it. What can you do with these two things right here? Add the exponents. Okay, it's just multiplying. The base is the same, negative 1. So I'm going to write one more thing on this. So let's write down we have series of negative 1 to the 2k times k. Now we're ready to start thinking about whether that converges or diverges. Okay? Now, this is what's important on this problem. Okay, so pay attention to this. If that's a 2k, what kind of exponent is that always going to be? Even. Good. Okay, so that really means, since that is an even exponent, that means that you're going to have the series, you can just look at that as negative 1 to an even power. Now, if you take negative 1 to an even power, what do you always get? You always get 1, right? So you know this is really just the series of 1 times k. Now think about whether that converges or diverges. Okay, what is that series? Okay, if you started k at 1, I didn't write down where k started on this, it would just be 1 plus 2 plus 3 plus 4. Clearly that diverges, right? Right? Okay, so that means that diverges. So what that means is on your interval of convergence, we're going to have a parenthesis around 2. So you don't include the 2. Okay, remember what we're doing is we already got the interval of convergence is 2 to 6, but we need to know if 2 counts or doesn't count. 2 doesn't count. That's the idea. All right, does that make sense?
How do we know that again?
Okay, because we got all, after we did all this algebra, that's the series we have. And just write the series out. What does that series really do? It just goes 1 plus 2 plus 3 plus 4 plus 5. If you added up an infinite number of numbers and they're getting bigger forever, then it's never going to reach a finite sum, right? Okay, gets bigger without limit. Does that make sense to everybody? Okay, sometimes at the end of the problem you might not recognize that series, but you can just analyze it mentally and tell whether it diverges or converges if it's pretty simple like that. Okay, all right, let's go to the next situation here. This is very similar. Now this one's going to be series -1 to the k times k. Now you're going to have 6 minus 4 or 2 to the k over 2 to the k. So what happens? What do you see? 2 to the k's cross out. That's kind of nice. Okay. So what we have is we have the series -1 to the k times k. Now you can't really simplify that any further, but you can think about what happens. Okay. I think I meant to write on here this was either k equals 0 to infinity or 1 to infinity. It doesn't really matter on this problem. So the idea with this is if you did this, if you just wrote out a few terms, you'd have like -1 to the 1 times 1. Then it would be plus -1 to the second times 2. Then it would be plus -3 to the second times 3. So that would be -1. That would be plus, what's that, like 8. 2 times 4 is 8. That's 9 times 3 is 27. Hold on, that's a third power is what that is. So now it'd be -27 times 3 would be minus 81. Now what do you think just by looking at that? Does that look like it converges or diverges? Is it ever, are the endpoints, as you go out further, what's happening to this number? It's getting bigger and bigger forever, right? So that means it's going to diverge. Okay, if that number clearly just gets bigger and bigger, if the terms are going to infinity, so is the series. So that one also diverges. Does that make sense? Okay, see both of those things at the very end, you just got to write these things out, write out some terms and think about it. Now what happens is, if you see that the terms are getting bigger forever, then you're going to know automatically it diverges. The only time it's even possible that it converge would be if those terms are going to 0. Now, if they go to 0, it doesn't necessarily mean it's going to converge, but it means there's a chance, okay? Does that make any sense? So the terms get bigger forever, what are you going to conclude? Diverge, good. Okay, so what does that tell us? That also tells us now that on your interval, 6 is not included, so it's a parenthesis. All right, so here is the grand conclusion of this problem. We say the interval of convergence is going to be 2 to 6, not including the endpoints. Okay, we say the radius of convergence, let's see if you guys got that or not. Okay, what's the radius of convergence? It's just the middle of this. If you look at the middle of this interval, what's the average of 2 and 6? 4. So you have like 2, 4, 6. The radius is just going from the distance from 4 to those numbers. So what is that? 2, right? Radius of convergence is just the average. The average of 6 and 2 is 4, and then the distance from 4 to 6 is going to be 2. All right? That's always in the middle of the interval like that. All right? So that just says if this series is centered at 2, then if you, the radius of convergence would be from the 4 to the 6 and from the 4 to 2 like that. That's the idea. Okay, what do you think? You guys follow what I did? I never know. Tell me. Okay. It's not too bad. Okay, there's a lot of little details in the problem. I'm going to run through a couple of more of these because there's a few other things that can happen on this. And let's go ahead and let's do a few more of these then. All right, so let's see what we have on the next page here. Now we're going to start this one out kind of the same way. Okay, so we have this series. Again, I'm just going to do a ratio test on this. On these problems, you almost always do a ratio test. You can occasionally try a root test if you want to. You could probably try a root test on here, but I'd probably go ratio test. Ratio test usually is what you use, just because that k right there doesn't have a power on it. If it had k to the k power, then I would probably be tempted to just use a root test, okay, like we've learned. So what we're ultimately going to do on this problem is, here's what we're going to do. We're going to show by the ratio test that the limit as k goes to infinity of, and we're doing absolute convergence, so we're going to say that the absolute value of a sub k plus 1 over a sub k is less than 1. So we're going to work out that limit, set it less than 1, solve that inequality to find that interval of convergence. That's the whole goal right there. When you're doing these problems, you want to get that in mind. All right? So let's go ahead and let's set up our ratio test. So that's what we're going to be doing. Okay, so with this, let's see, we have the limit, k goes to infinity, and let's see, when we put this together, okay, let's go ahead and just go ahead and do a sub k plus 1. What's a sub k plus 1? What does that mean? Make the k go to k plus 1. Every k in the series goes to k plus 1. Okay, 3 to the k is going to go to 3 to the k plus 1. K is going to go to k plus 1. All right, so we got that. Now, you're going to divide, so what that part right there is that's this, okay? We just did the a sub k plus 1. Now you're going to do the a sub k, but since you're dividing it, you're really multiplying by the reciprocal. Everybody good with that? That's why I'm going to start doing these, okay? Just do that in your head. You know that that's the way that's going to be, okay? So we're going to work with that, and we're going to work out that limit, and then kind of see where that takes us, and then we'll set that less than 1. Okay, so the rest of the problem sort of becomes an exercise in a lot of algebra, so we need to kind of see what we can do here. I recommend you just break all this up as far as you can. So if you do this, this term right here is going to be x minus 1 to the k times x minus 1 to the 1. So you want to start that way. Just put it all in one big fraction. Then you have 3 to the k. Leave it alone. You have k. Leave it alone. Okay, go to the bottom where you have 3 to the k plus 1. How are you going to break up 3 to the k plus 1? 3 to the k times 3 to the first. Okay, everybody see what I'm doing? Okay, now let's see, what do we have here? We have k plus 1 here, and then we have times x minus 1 to the k. Almost always when you work this out with a ratio test, you find some things start just dividing out. So let's see what we have that cancels out. So it looks like that's going to go away. Okay, what else? 3 to the k goes away, and everything else is different, okay? So now, what we want to be real careful about is, let's identify everything inside that could go out of the side of the limit. Can you tell me what would go outside of the limit, all the constants? Okay, that's a constant. Everybody got that? Why? Because it has an x in it. How about 3? Sure, bring it out, okay? That's kind of a good approach. So I'm going to take that x minus 1 to the first over 3 out of what's left over. Then what I'm going to have is I'm going to have the limit as k goes to infinity, and I'm going to be left with, after I take those things out, okay, they don't cancel, they're taken out, you'd be left with k over k plus 1 then, like that after you do that then, okay? All right, so I think I'm on the right track here. All right, everybody okay so far? Okay, all right, now what do we got to do? We just got to do this limit, okay? So tell me what the value of that limit is in your head. It's 1 again, okay? Happens a lot, okay? So that's going to be 1. You can use L'Hopital's rule, or you can just see that the coefficients are 1 over 1, like you've done. So that's going to leave us with absolute value x minus 1 over 3 times 1, like that, okay? Or that's just going to be absolute value x minus 1, then what are you going to do? To make for the condition for convergence is less than what? 1. Okay, that's what you're always going to do on a ratio test. You're going to take that absolute value, that whatever expression you end up less than 1, then you're going to solve it. Okay, so let's go ahead and solve this then. Okay, so we solved the inequality. So the way you're going to do this then is you're going to do negative 1 less than x minus 1 over 3 less than 1. Okay, very similar to the last problem. Let's do this real quickly. Just multiply everything by 3. Okay, and when you do that, that's going to give me, it looks like, negative 3 less than x minus 1 less than 3. Then you can add 1 to each part. And if you do that, you're going to get negative 2 less than x less than 4 like that. Okay, so that is a potential interval of convergence. We're not done with the problem yet, but let's kind of talk about what we've done so far. All right, now what does that mean? In this problem, you have a range of places where this converges. That means x. If x is between negative 2 and 4, then this whole series will converge. If it's outside of that interval, it's going to diverge. That's what we just showed by the ratio test, really. Now, what else do we got to do? Don't forget this piece. What did I do on the last problem? I tested the endpoints to see if I include them or exclude them. So the question becomes, you know, do I include the negative 2 or the 4? Okay, so you have to actually test that out. So that's the next piece we need to do. So you don't forget about doing that. You've already done most of the problem. So what we're going to do is we're going to let x be negative 2. Then we're going to be let x equal 4. And what we're going to do is, where do we go with that? We go all the way back to the beginning. So you want to look at the original problem. That's what we're going to test, is that. We're going to let x be those endpoints of the interval of convergence and see what we get. Okay, so let's do this then. We have interval, you don't have to put k1 into infinity necessarily on this. So we have negative 2 minus 1 to the k over 3 to the k times k. We need to work that out and see what's going on in the problem, okay? Keep working it out. I'm just going to write down the series. So that's going to be negative 3 to the k all over 3 to the k times k, like that, okay? Now, the algebra, what could I do with what I just highlighted there? You can put it in one big thing. You can write negative 3 over 3 all to the k, right? You're going to do this a lot when this shows up. You need to really make sure you pay attention a bit and you're able to do this. So you write that as negative 3 over 3 to the k power. And then really you have 1 over k if you want to write it like that, okay? So that's going to give you series negative 1 to the k times 1 over k. Okay, now let me see if we recognize this. I mean, we're to a point where maybe you're beginning to recognize some of these things. Okay, what if we had this? Let me talk through it this way. What if I didn't have this? What is that? That's a harmonic series, right? Which diverges. But what does that cause that to do? Alternate. We did talk about alternating harmonic series. It actually converges. So if you don't know that, you want to know that. That's an alternating harmonic series. That's one of the ones that we learned convergence, okay? So you got to learn to spot these things, see, okay? So that is going to be, you might want to make a note that that's an alternating harmonic, so that converges. Okay, now what does that tell us then? That tells us that we include the negative 2, okay? So we're now going to have a bracket on the negative 2 when we do that, all right? Does that make sense to everybody? Okay, now let's do the 4. Go back to the beginning, and we're just going to do the series. We're going to plug it 4 minus 1, plug in for x. So we have 4 minus 1 to the k over 3 to the k times k. So that's the series 3 to the k, like that. That's going to cross out. Those do cross out, so we're left with this. Okay, what kind of series is 1 over k? Harmonic. What does harmonic do? It diverges. Good. Okay, so that's a harmonic series. Therefore, it diverges. Okay, so what are you going to do with that 4 then? Are you going to do a bracket or a parenthesis? Parenthesis. So that is your interval of convergence right there. Okay? So sometimes you'll end up including one or both. It all depends. You don't know until you work out the details. So what you would have on this, the conclusion would be your interval of convergence. I'll just abbreviate that. Interval of convergence is bracket -2, 4. And what that means is this power series is going to converge on that interval. So if you worked with -2, if you plugged -2 in to the original series, it'll cause it to converge. If you plug in 4, it will not converge, but anything between -2 and 4 will cause it to converge. Everything else diverges, okay? Now, the other thing I want you to be able to do is the radius of convergence, okay? So what you really can do on that is, you can kind of look at this like on a number line if you want to, whatever. You can just do this. Here's 0, 1, 2, 3, 4. Here's -2. Okay, so that's your interval of convergence right there. The middle point of that is where? 1. Okay, so let's see if you just do this. If you just go through and take up that, the distance between those numbers is going to be 6. And then if you take 6 divided by 2, you get 3. Okay, all you got to ever do is just find the distance between the interval and divide by 2. So that radius of convergence is going to end up being 3 then. Okay, so that's the idea. Okay, how does that look? Okay, that's the kind of thing that you'll be doing when on your third exam. Very similar things like this. It'll be kind of things where at the end of the problem, usually what happens on the end of the problem, you might come up with harmonic series, alternating harmonic, or just things like the last example that you could tell diverge. Okay? All right, any questions about that? Okay? All right. So I'm going to do one last one. We haven't done one quite like this one yet, so I'm going to go ahead and do that. And then we kind of have a second part of this that I want to start looking at also. Okay, so with this, we are going to do exactly the same thing. Okay, so this time something a little different is going to happen. Okay, so what we're going to do is, like all these problems we've been doing, we're going to show that the limit k goes to infinity. We're going to do the ratio test again. So the ratio test, the condition for convergence is this. Now see, what we're really doing is we're really doing absolute convergence on this. Okay, but we're applying the ratio test. So what we're going to do is we're going to show that the absolute value of a sub k plus 1 over a sub k is less than 1. That's the condition for convergence in the ratio test. Okay, so what we're going to do is go ahead and get this set up in your ratio test then. Okay, so I'm going to have this. A sub k plus 1, that's just going to be x to the k plus 1 over k plus 1 factorial. Okay, so that's what that piece is. So we've got that established now. Okay, now the next thing we're going to do is we're going to divide by a sub k. Well, a sub k is just the original series, but since we're dividing by it, we're going to multiply by the reciprocal. Okay, so that's going to be k factorial over x to the k like that. So that's the setup of the ratio test, all right? Now, what we need to do is we need to kind of break some stuff up, see if things cancel. That's kind of the general thing you always do. So it looks like we're going to have limit k goes to infinity. Okay, the x to the k plus 1, how do you write that? X to the k times x to the first. Okay, now the k factorial, let's think about that a little bit here. I'm going to leave that alone for now. You could write that as k times k minus 1 times k minus 2 if you wanted to, if you needed to. What I'm going to focus in on is this thing. This thing shows up all the time. So when you do this, when you do a factorial, what do you really do? You always write down the first term, right? Whatever it is. And then what do? The next term is going to be 1 less than that, which is what? K. But wouldn't it be k factorial? Okay, does that make sense? Okay, you write the first term down. X plus k. I mean, just think about if you had this, 7 factorial. What do? You write the first term down, and then it's times 6 factorial, right? That's what I did. I wrote the first term down, and then it's the next term lower than that factorial. So that's going to end up just being written as k plus 1 without a factorial times k factorial. Then I have the x to the k like that. Does this make sense? This is an area students a lot of times overlook. That thing, just that little piece right there.
So if you had k plus 2 factorial, would you have k plus 2, k plus 1, then k factorial?
Let's see, where are you looking here?
I'm saying if you had k plus 2 factorial, would you have k plus 2, k plus 1, then k plus
Oh, yeah, okay, so you're saying if you had k plus 2 factorial.
Yeah.
Well, you could write that as k plus 2, then go 1 less, k plus 1, then you're at k, so you could just put k factorial. That's what you said, right? Yeah, good, so you've caught on to it, okay? Now what you're trying to do, the reason you do that is because you're trying to get something to cancel out. Now, if you just wrote the terms out, you'd get the same result anyway. Okay, so let's see, what goes away? The k factorials go away, which is nice, and that goes away. Okay, so we got that. Now, look at what you're left with, okay? Tell me what, after we're left with, what will come out of the limit? The x, right? Okay, that's treated as a constant that comes out. Okay, whatever has an x comes out. So you're going to have x in an absolute value, it's still an absolute value, that's important, times the limit as k goes to infinity, and it looks like what we're left with now after that is 1 over k plus 1. Okay, like that. All right, so that's what we should have at that stage. Now we're ready to go through and just work out the limit then, okay? All right, so we got that. All right, what's the value of this limit? This is kind of weird. 0, right? Okay, the degree of the top is less than the degree of the bottom. It's going to go to 0. All this really means is this is just basically 1 over infinity. The numerator stays the same, so it's just 1 over infinity, so that goes to 0. So what you have is you have absolute value of x times 0, which is obviously 0. Okay? Well, that's kind of weird. We haven't seen that yet. What we've seen so far is we've been getting some expression that we could set less than 1. Well, we still do the same thing technically. The result is 0. We set it less than 1. Isn't that always true, that 0 is less than 1? Okay, so you're not going to have anything you solve. This is going to cause you to conclude that the interval of convergence is going to be this then. Okay, so the interval of convergence is all real numbers. So it's negative infinity to infinity. Remember what we were trying to show. Don't forget at the very beginning of the problem, we were trying to show that that limit by the ratio test was less than 1. Well, it was. 0 is less than 1. Okay, so that just means that it always converges. If that happens, that's got to be the case. Okay, the radius of convergence, what do you think that would be? It'd have to be infinity, right? Okay, so we'd say the radius of convergence is r equals infinity also like that. And that's it. Okay, that's the idea. Now, I was going to show you just one little thing on this, is that's the result of the problem right there. So if that happens, that's another thing that can happen is, well, this power series always converges. Okay, that's what we come up with. Let me show you this. You don't necessarily have to write this down, but just to show you something on this, what this means if we picked any number for x, it would converge. Let's just see what happens if x is equal to 1. Let me show you what would happen. Okay, if you wrote out the terms, you would actually have this. You would have 1, if x is 1 now, you'd have 1 to the 0 over 0 factorial. Next term would be 1 to the first over 1 factorial. Then it would be 2 to the first over 2 factorial. And then 3 to the first over 3 factorial and so forth like that. Now what would end up happening on this if you went all the way out like this term right here is, notice that the fractions, aren't the fractions getting smaller as we go out? Because 3 factorial is big. I mean it's 6, so we get that. But if you went way, way out here, eventually you'd end up with like 10 to the first over 10 factorial. 10 factorial is way bigger than 10, right? So what's happening is these terms are going to 0. Okay? That doesn't necessarily by itself mean it converges, but it does show you that those terms are just getting to 0 as they go out. So that would happen no matter what x is in this problem. That's the idea. Okay, pretty abstract, but that's the idea. Okay, does that make sense? Okay, all right. So let's see, on the next page, let's see, we're going to do, let's see, there's a couple of things we're going to do on this. This is the remaining part of the handout. We start looking at building series. So we start looking at that a little bit here, okay? So let's see where I'm at here. So I want to do these examples and kind of get this 9.2 part wrapped up here. Then we do have a second part of this too. So let's go ahead and let's get this done. Okay, so here's what we were working on. When we were working with a power series, like this, here's what we found so far. We did one problem where the radius of convergence, the interval of convergence was all real numbers. We did that. We also did some problems where we just got a finite radius of convergence. Okay, we did several of those. We had a radius of 3, radius of 4, whatever like that. You could also have one where the series converges only at one number. Okay, if it only converged at one number, then that would mean the radius is equal to 0. The interval is just that number. Well, that's it. Those are the 3 possibilities that exist. So we've done 2 of those 3. Okay. So what we're going to look at next here is the idea is if you have a power series, you can do this. This says the sum and difference, the power series is going to converge absolutely if you just add up those 2 functions. So if you have 2 functions added, then you can just break that up into a sum and difference. You'll see what I'm talking about on this when I'm doing a couple examples. Now this is stuff you already really know from a series anyway. You can take constants out and everything, okay? And then we can work with compositions. I'm not going to go into that very much in depth because the examples I'm going to do are going to illustrate that anyway, okay? So what we're going to be looking at here is this problem. We're going to use a geometric series, which we know that's a basic geometric series, to find the power series representation for this function centered at 0. So we're going to actually turn this function. That's just a function like you've learned about before, like in college algebra. We're going to turn that into an infinite series, okay? So the idea is, the first thing I want to make sure that you understand in this problem is that this is if you had 1 over 1 minus x. If you had that, that would be the same thing as a geometric series, like that. You're used to seeing a geometric series written out, like this. Okay, you're used to seeing it like that, correct? All right, and you've learned the formula that if if the absolute value of r is less than 1, which just means that the geometric series converges from -1 to 1, then that's how you find the value of that convergence. Okay, is a over 1 minus r. Does everybody remember that formula? Okay, so what we're doing with that is we're just replacing like that r with an x. Okay, we're just replacing variables. So we're saying as long as x is between -1 and 1, then this function, 1 over 1 minus x, could be represented by that power series. Okay, because it's the same thing. Okay, it's a geometric series. So notice the problem we're going to do, it has the same denominator, doesn't it? So what we're going to end up doing with this is we're going to break this up kind of into a power series like this. So here's the basic idea with this. One thing that you want to note on this basically is that x to the third times, and I'm going to write it like this, times 1 over 1 minus x. The reason we're doing that is so we can compare this to this geometric series. That's going to be equal to this right here. That's going to be equal to the series from k equals 0 to infinity, like we have on the geometric series right here, of basically of x, like this. Okay, this thing right here is going to be x to the k. That thing right there by itself will be x to the k. All right, however, if you went through and added this in, like that, then what you would get is you would get the series k equals 0 to infinity of x to the k plus 3 like that. So that still has the structure of a geometric series. It's still x to some power like that, okay? So what we're going to go ahead and do is we're going to do these things on this problem. So what we're going to do is we know this converges. Since this is a geometric series, what's the condition for convergence on a geometric series? -1 to 1. So this is going to converge on -1 less than x less than 1. Now we're not using r, we're using x. Okay, same thing. Okay, so we have that, so it's going to converge on that. So what we're going to do with this then is we're going to look at, we're just given the interval and convergence on this new series. So what we're saying is you can break that x to the third up. See, that x to the third can be treated like a constant. That's why that thing can just go within the series like that. So we're going to look at what happens at x equals -1. We've already got our interval of convergence because it is a geometric series. Okay, x to the k plus 3 is a geometric series. Okay, so the idea with this is going to be, we just need to see if we need to include those endpoints or not, like we did on the previous problem. So what we end up doing is we plug in, we're going to work with this series, we're just going to replace x with -1 and see what we get. So we would have series k equals 0 to infinity of -1 to the k plus 3, okay, like that, all right? Then if we do that, we're going to end up having, you can break this up as -1 to the k times -1 to the third, like that. So you can break that up. We're just seeing if this series converges or diverges. So there's a couple of things that you could do on this. First of all, this thing right here is a constant, right? So if it's constant, we know that can come out. And that's really -1. -1 to the third is -1. So we could write that as -1 times the series k equals 0 to infinity of -1 to the k. So you need to draw the conclusion, does this thing converge or diverge? Think about it. Okay, all that is this series, if you wrote it out, what would it be? It'd be like -1 to the 0 plus -1 to the 1 plus -1 to the 2 and so forth forever and ever. What's that going to be? It's going to be 1 minus 1 plus 1 minus 1 plus 1 minus 1. Okay, that diverges. And the reason it diverges, although those terms keep canceling out, when you get to one more term, you always have a 1 or -1. So this one right here is going to diverge. So that means in your interval, which is this right here, come on, work. Okay, right there, would you include or exclude that -1? Exclude it. Okay, so we do that. We're doing the same thing. We're just working with a geometric series. Okay, now what we do is we work with x equals 1. Do the same thing. Plug in. This is the series we're working with right here. Okay, that's what we transformed that into. So we're going to have the series from at k equals 0 to infinity. And then we're going to replace this x this time with 1. So we're going to have 1 to the k plus 3. Okay, you can do this the same way. You can just write that as series k equals 0 to infinity of 1 to the k times 1 to the third. Well, that's really just the series k equals 0 to infinity of 1 to the k, right? Because 1 to the third's 1, so that just gives that. Okay, do you think that series converges or diverges? What is 1 to the k? It's 1. 1 to any power is 1, right? So what you really end up with is the series 1. That's just 1 plus 1 plus 1 plus 1 forever and ever and ever. So clearly that one diverges. Okay, so that would be the answer on that then. So that would mean that the interval of convergence, after all this stuff, what we conclude basically is the interval of convergence is going to be -1 to 1 without including the endpoints. Okay? What's the radius of convergence on this? What's the half the distance from -1 to 1? 1. Okay, so that would be radius equals 1. Okay? Radius of convergence is always half the distance between the endpoints of the interval. That's it. Okay? So what was a little bit different about this one is we're basically transforming this thing into a power series. Okay? Because we know this thing right here is the result of a power series. Does that make sense? Okay, some of these things right here, these problems right here are kind of hard to tell how well students understand them. See, basically in your basic geometric series, we were looking at A was 1. So we were looking at 1 r to the k. So it's 1 over 1 minus r. Well, if we change r to x, we get 1 over 1 minus x. That's what I'm doing. Okay, does that make sense? Okay, tell me, I don't know. Some of this stuff is real abstract to students. This part of the section's a little bit harder, I think.
So we just have to recognize that 1 over...
You do. And that's a real important connection to make, is because when you start looking at the examples I'm going to do, most of them are going to have that 1 over 1 minus x somewhere embedded in the problem with some algebra piece. This just had an extra thing. It had an x to the third. And what this property up here, when you're combining power series, that's what that was saying, is like if you have x to the third, that can be multiplied, that can be brought in to the series. That's what that's saying. That x to the third I brought into the series. And the reason you're doing that is because that's treated as a constant. You can bring a constant in a series or out of a series. That's what you've been doing anyway. Okay? Okay, let's work a little bit more with a few more of these and kind of see what we have going on these. These are a little harder to do. So with this one has the structure of the answer to a power series. So first of all, let's write this kind of down like this. Over at the side, let's just write down the geometric series so that you can see how this goes. The geometric series that you're familiar with is ARK, and it converges on the interval -1 to 1. Okay, that's what you learned about geometric series. And what was the answer? A over 1 minus r, right? Okay, now see, what you guys need to understand is this thing kind of has the same structure, doesn't it? Every problem I'm going to do is going to have a similar structure. That's the point behind that. So what we're going to go ahead and do with this is, let's think about how we turn this into this. Well, really, you would do this. That thing right there is kind of like the A, right? So we would have, you could think of A just being equal to 1, like on that, okay? So in this, A would end up being equal to 1. Okay, what does this thing, what do you want to turn that into? It needs to be x to the third. Okay, so that's kind of like your r right there. Okay, so that's going to just be r equals x to the third, like that. So what you're going to do is you're going to replace that r with x to the third like that then. Okay, and what we're going to do is we're going to write out what we have now. Okay, you got to kind of find the connection. So what we're going to have is we're going to have this thing becomes 1, a is 1, and then r becomes x to the third. So that's going to be equal to this, the series k equals 0 to infinity of, we said a was what? A was 1. So we're going to have 1 times, and we said r was what? X to the third. So we have x to the third to the k. So see, this particular mathematical function can be written as this series. It can be written as that power series, like that. Does that make sense? I'm doing straightforward substitutions. A over 1 minus r turns into 1 over 1 minus x to the third. Therefore, ar to the k turns into 1x to the third to the k. Does that make sense? Substitution. So you have to make the connection of how they relate to a geometric series, then we can begin to put that together. Okay, so here's our conclusion so far. We're going to say, therefore, 1 over 1 minus x to the third is equal to the series x equals 0 to infinity of x to the third to the k, like this. And then once we get that put together, we're going to do basically this. We're going to find an interval of convergence on that then, okay? So we got to kind of think about what test we might want to use. You can use a ratio test on this, but there's a better test for this situation. What do you think? Root test. Why root test? It's got a k power. The whole thing's got a k power. Okay? So what we're going to do is we're going to show this. So ultimately in this problem, what we're going to do is we're going to show that the limit as k goes to infinity of the k root, and we're going to do absolute value again, of a sub k is less than 1. That's a condition for the root test, okay, like we've learned. Okay, let me write that a little bit better. That's supposed to be an a to the k power like that. Okay, so we're going to just basically work with that root test now, okay? So what we're going to have here then is when we do this, let's go ahead and do the limit as k goes to infinity, and we're going to do the k root of this. So we're going to do the k root of the absolute value of x to the third to the k, like that. Okay? So what's the k root of anything to the k? Itself, exactly. Okay? Now remember, you're just doing 3k over k. Okay, you can write it that way if you want to. So this is going to be the limit. You can do this in your head, but just to show you, what we're really doing is absolute value of x to the third to the k over k. All right, right? So that's what we're doing. Okay, you're always, no, hold on. That would be x to the third, k over k gives you 1. So that's going to be limit k goes to infinity of absolute value of x to the third. Okay, we just did the k root of something to the k power. It undid itself. Okay, all right, are you with me so far? Okay, now, technically what you can do on this is, this whole thing right here is a constant, right? There isn't any k's in there, so what can you do with that x to the third? Move it on out, okay? It's a constant, take it out. So what you're going to have is absolute value of x to the third times the limit as k goes to infinity of 1. Okay, you're left over with that. The limit of 1 is what? 1. Okay, so you would end up with just x to the third times 1, or just absolute value of x to the third. Okay? All right, now what is the condition for convergence on the root test? Less than 1. So what we're going to do is you're going to take this thing, and you're going to set that less than 1 like that. All right? Now, what we do with this is we really just do this. We really just say -1 is less than x to the third, and we don't do absolute value anymore. That's gone, because remember, when you set up this inequality, work. Okay, that's just now going to be x to the third less than 1. Okay? Well, how do you undo the third power so it just becomes x? Third root. Okay, third root. And it doesn't matter. You can do a third root of a negative or positive number. So we're going to go ahead and do the third root of each side, each part. Okay, so that's going to end up giving you -1 less than x less than 1. Okay, so that would be your potential interval of convergence. Okay, so we got that now. Now what we got to do on this is you have to go through and test the endpoints. Okay, so that's the next thing. That's what you're always doing on this. If you're getting an interval of convergence, you got to test those endpoints. Okay, like that. Okay, all right. So let's go to x equals -1. And let's go to x equals 1. Okay, now the series that we're doing was, let's see, where's my series? Right here. Okay, this is what we're doing, is we're testing in this series. Okay, that's what we're going to test, is we're going to use that. Okay, so what you need to do is go ahead and when you test -1, you're going to do the series of 1 to the third to the k. You don't have to write down the x equals, or that should be x equals 1 to infinity. Don't worry about that. So that's going to be the series 1 to the 3k, okay, which is what? What's 1 to any power? 1, okay, all right. Or you could do it this way. I mean, you can just say 1 to the third's 1, so you'd have 1 to the k. So that's really just series 1 to the k. So that's the series. I hate it when that happens. Okay. Got the series of 1. Okay, does that diverge or converge? Diverge. How come? What is that series doing? It's doing 1 plus 1 plus 1 plus 1 forever. Okay, The endpoints of those terms are not going to 0. So that diverges, which means that you're going to have a open interval on the -1. Okay, you do the same thing for 1. So now we do series. Again, we're going to do, I forgot to put a -1 in there, didn't I? I wasn't even paying attention on that. Yeah, let me show you something on this. I think I'm still okay on this, but I don't know why I did that. I was kind of getting a little sloppy here. Let me close OneNote. OneNote's kind of screwing up on me again, like it always does. But what I did on that first interval of convergence, I plugged in a 1. I didn't plug in a -1. I think it's still going to diverge, but I need to make sure we get that right. Okay, so here's what I'm going to do. What I just tested, just to save a little bit of time, I just tested 1, right? I didn't plug in a -1. I plugged in a 1. Okay, so we're going to have an open interval on the 1 for sure. Let's go ahead and let's test the -1. Let's just do this correctly. So now what you would have is your series was, it was like -1 to the 3rd all to the k. You can write it that way if you want to, okay? It was basically we were doing x to the 3rd to the k, all right? So if we do that, what we would have is the series of, and then the result of -1 to the 3rd is -1, so we'd have -1 to the k like that, okay? Now, what does that series do? If you wrote out the terms on that, what would it do? It would alternate, so it would go like, it would go -1 to the 0 is 1, but it would just alternate, and a lot of times students think that's going to go to 0. Remember, yeah, the terms will cancel, but you always have another term, don't you? Okay, so that one also diverges, so that means that's also an open interval. So what that means in this problem then is this would be our conclusion, is we would have this. The interval of convergence is going to be -1 to 1, okay? That means -1 and 1 are not included. Now tell me what the radius of convergence is then. That's 1, okay? The distance between -1 and 1 is 1. Half of that's that. See, the radius is always just this. 1 minus -1 all over 2. That's what you always do. Subtract the two numbers, divide by 2, and it's a positive number, so that would be 1. Okay, so that's how that kind of goes. That would be the basic idea. I'm going to go ahead and do one more of these, and then we'll take a break, because that'll kind of get me through this type of problem. The next one's the same idea. Might be a little harder, but the idea is we're trying to look at things that relate to a geometric series. Okay? Okay, at first glance, remember what we're looking at is 1 over 1 minus x. Well, that kind of looks like that, except it has 1 plus something, but we can massage it a little bit, translate it into that geometric series. So let's start. I think a good starting point on this is let's just write down the geometric series formula. We have summation AR to the k goes equals 0 to infinity, and we said when r is -1 to 1, let me write this like this, okay, we know this converges to what? A over 1 minus r, right? Okay, that's what you've got to know. That's why I kind of put this down here and printed this out again, is that you need to know this, and then that convergence of a geometric series. Now what we're going to do is we're going to establish some connections on this, okay? This thing right here is what A is, right? So A is equal to 1. So that means we're going to replace A with 1 in that formula, like that, okay? Now what this is going to be, this denominator is really going to be 1 minus -4x, right? Why am I doing that? So it'll match with 1 minus r, right? So tell me what r is in this problem. -4x, good. Okay, that's important. So that's what your r is. So r is going to be -4x. The key thing is you want to get this geometric series set up like that. Okay? So see, what we're trying to do is we're trying to compare that function, that rational function, to a over 1 minus r. Every problem I've done so far has had a constant in the numerator and either 1 plus or 1 minus something. Okay? Some kind of expression like that. So what you're going to end up with then is you'll end up with this. You're going to end up with 1 over 1 plus 4x is equal to the series from k equals 0 to infinity, and then a is going to be 1. I'm going to put the 1 in there for emphasis, and then r is going to be negative 4k to the k power like that. That's step 1 of the problem. That's substitution. Tell me if you've got that. It's all recognition of patterns is what's going on in that problem. So you've got to see that you can translate this function into an infinite series that's a geometric series. Now what we're going to do is we're going to find the interval of convergence on this, okay? Now I did make a mistake right there. I don't know why I put a negative 4k there. And the reason I caught that is because I knew I needed a variable x in there. So what I'll end up having is negative 4x like that, okay? So what we're going to do is we're now going to look for the interval of convergence. Okay, so what you have to do on the interval of convergence is you got to decide which test you're going to apply. Okay, we could do a root test, we could do a ratio test. It doesn't matter. I think I'm going to do a ratio test on this. It should work either way. I'm going to go ahead and just do a ratio test on this. Okay, so when I do this by ratio test, okay, what we're looking at is we know that we need to show on a ratio test that the limit as k goes to infinity of this thing right here by ratio test is of a sub k plus 1 over a sub k. What does that have to be less than on a ratio test? Less than 1, okay? So we have that. So we need to set this up, and then this will lead us to figuring out that interval of convergence. I think the root test would probably work well on this too. But part of the reason I'm bypassing that's because of that negative. I'm not sure how that negative would work out. So let's go ahead and get this put together. So this is going to be limit k goes to infinity. Okay, we want to go ahead and do the a sub k plus 1. Okay, all that's going to be is just negative 4x k plus 1. Don't worry about the 1. The 1 doesn't make any difference. You multiply anything by 1, it's itself. Okay, then we want to do the a sub k, which is the same thing. Now we don't need to do a reciprocal, we can just, because we'll have a normal fraction. So what I'm going to put there is negative 4x to the k like that. So that's the ratio test, and we're wanting to show that that's less than 1. So I've got my ratio put together, okay? So let's go ahead and kind of work with this and see what we have. So this is limit k goes to infinity. Tell me how you should break up this numerator. Negative 4x to the k times what? Negative 4x to the first. I would do that all the time. So negative 4x to the k times negative 4x to the first all over negative 4x to the k. All right, what do you see happening here? Got to cancel. That almost always happens on ratio tests. Okay, so what I'm going to end up with is that's going to leave me with the limit as k goes to infinity of absolute value of negative 4x to the first, which is just itself. Okay, like that. Okay. So when we do this now, okay, well the absolute value of negative 4 is 4. So you could go ahead and write this like this. Okay, I mean you could bring that out. You can bring the whole thing out of the limit if you want to. But isn't that the same? Of course, because the absolute value of negative 4 is 4. You can do that if you want to, or you can do it later, it doesn't matter. Okay, now, what can you do with the 4x? That can come out of the limit because it's a constant. Both 4 and x are constants, so what you really have is you have absolute value of 4x times the limit k goes to infinity of 1. Okay, what is the value of the limit of 1? 1. Okay, so what you get is you get 4x in absolute value times 1. So that's the result. Okay? So that's what the ratio test leads us to. So now what we're going to do is we're going to just take the result, which was absolute value 4x, set it less than 1 because that's a condition for convergence using the ratio test. So what you're going to do now is solve the inequality. So that's negative 1 less than 4x less than 1, like that. Then you can divide by 4. Okay, so it looks like your interval of convergence is going to be -1/4 to 1/4 like that. Okay, so we got that. All right, now what's the last thing we got to do here? And then we're done. Got to test the endpoints. Okay, so we need to test x equals -1/4. Then we need to test x equals 1/4 like that. So you want to go back to your series. The series we're going to be working with was, where did I write that down at? That's here. That's what I got boxed in right there in red. Okay. You do these problems, you got to kind of keep track of stuff. So I'm going to test in that series. So what I'm going to get is the series, and then that's going to just be -4 times -1/4 to the k power. So we're doing that. You're just plugging in for x. Okay, then we're going to do the same thing for 1/4. That's the series -4 times 1/4 to the k power. Okay, and we'll see if they diverge or one of them converges or whatever. Okay, all right, so this is pretty easy to do. Okay, if you do this, this is 4/4. So that's really the series 1 to k. Right, that's positive 4/4. What does that do? Converge or diverge? Diverge. How come? You're adding ones, exactly, perfect. 1 plus 1 plus 1 forever, it gets bigger and bigger without limit, okay? So that diverges. Okay, the next one is just going to be -1 to the k. How about that? Does that converge or diverge? Diverge, how come? Because it's -1 plus 1, alternating series. You have all that cancellation, but you still get another term, no matter how far out you are in the series. So that also diverges. So now what we can do is our conclusion is going to be basically this. Okay, we conclude these two things. The interval of convergence is going to be -1/4 to 1/4, like that. And then we got to figure out the radius of convergence. Okay, what's the middle point of that interval? 0. How far is 0 from 1/4? 1/4. Okay, so that radius of convergence is going to be 1/4 like that. Okay. Okay, so you can just do that. Now, the radius convergence, you can even just draw a picture on a number line and figure it out that way. All right, that's the conclusion. Okay. All right, so let's go ahead and do a break here. There's a second part of this that we're going to run through when we get back. This is first of all. Okay, so what this is saying, now you don't need to write this down because this is on D2L, this theorem and everything, but I would at least like you to write down kind of the solutions of what I'm doing so you can follow along okay. So the idea is if you have a power series, you can differentiate a power series and get a series for that derivative. You can also integrate a power series and get a new series built on that, because when you're differentiating a function, you're getting a new function. So if you differentiate term by term in the series, you're going to get a new series. So the idea with this is basically this is a general power series right here centered at A. So like we say we have like a center at A. And the idea with this is you can differentiate this, and when you do, if you differentiated this, you would get this new series. Now this is not that hard to see in your head. I mean, c sub k is a constant, right? So if you were differentiating this, I'm going to go through a little bit more extensive showing you where this comes from, but if you just were differentiating this right here, how do you differentiate this? This is a chain rule, right? You would just go bring the k down, you would have x minus a to the k minus 1, then you would do the derivative of the inside part, which would be 1. So that's where that piece right there comes from, and that c of k is just a constant. That's what that is. If you're doing this one, if you're doing if you're integrating this thing, if you did the integral of x minus a to the k, well, what do? You do power rule. You would just say x minus a to the k plus 1 over k plus 1. Now, I'm going to show you where that comes from. And again, you don't have to have this in your notebook, but I do want you to at least just get a piece of paper out and write down kind of what I'm doing, because I do want to show this to you, this type of stuff does show up in higher math and diff EQ a little bit. There's going to be some of this stuff in series that you will see again in diff EQ, particularly power series. It's a big deal in differential equations. So what I want to show you on this is basically I want to just run through kind of the development of this first thing right here. I want to show this number 1 and what it's really saying on here. So what I want you to start off by is just write down that you have f of x equals the series k equals 0 to infinity of c of k and then x minus a to the k. That's just kind of your formula for your general power series like this, okay? All right? And pay attention to this. This is not that hard, but I'm going to try to show you what happens when you do the derivative of a series, of a power series. So what we're going to do is let's write the terms out, okay? So if k was equal to 0, just try to think in your head what you would have. You would really have c of 0, which is just a constant. Then you would have like x minus a to the 0, which would just be 1. That whole thing would be 1, so that first term is c of 0. All right? If we go to k equals 1, then what will we have? If k is 1, you would have c of 1, right, which is just a different constant. Then you would have x minus a to the first power like that. And then so forth. Let's write like 2 more terms out. What's the next one? The next one's going to be c of 2, a new constant, x minus a to the second, plus, and then a new constant, c of 3, x minus a to the third like that. Then it's going to go on and on and on, and then eventually you're just up to the general term, ck, x minus a to the k like that. Okay? So, everybody understand how that's being written out okay? Okay, now what I'm going to do is I'm going to show you that when you do a derivative of a power series, you do it term by term. And here's what we're going to do on this. So this is stuff you already know. Okay, what would be the derivative of c of 0 since it's a constant? 0, right. Okay, so that's going to be 0. That's the first term in this series for the derivative. Okay, now let's do this one. Okay, that's a power rule. What would be the derivative of that? You'd write down the constant c, right? If you have a constant, you write it down when you do a derivative. What's the derivative of x minus a to the first? Because that's just x minus a, right? All right. So what's the derivative of x? 1. What's the derivative of 0? Or of a? 0. So what I'm saying is this whole thing right here, that derivative is just going to be c1. If you don't want to look at it that way, you can look at it this way. That's c1x minus c1a. That derivative c1, that derivative 0. So that's just going to be c1. Okay, what we're doing is we're differentiating term by term each part of that series. That's the idea. Okay, now the next one. This one's easy. How are you going to do that derivative? Well, you're going to bring down the 2. You're going to have 2c2. That c2 is a constant, so you write it down. Then you would have x minus a to the first power. The chain rule would say do the derivative of what's inside, but that's just a 1 anyway, so you can ignore that. Okay, what I'm doing is just doing a general derivative as I'm going through this then. Okay? All right. Now, if we did the next one, so if we go to this next term, it's going to be the same thing. We got that done now, so let's do this term. So what's this derivative going to be on this term right here? Tell me what that is. 3c to the third times what? X minus a to the second. Okay, everybody got that? Okay, that's stuff you know how to do. Now, eventually, when we get way, way out to the end, well, what are you going to do on this term? You're going to bring down the k, so you'll have k c sub k, x minus a to the k minus 1. And that's what that theorem is saying. That's what that formula is. So what you end up getting, therefore, you have a new series for the derivative. So if you have a function that's represented by a power series, you can get a series when you differentiate it. And that new series is going to be k c sub k, you're going to have the series like that, x minus a to the k minus 1 like that. Okay, we're doing that term by term. Does that make sense? Okay, I'll do a couple of specific examples on this in just a minute to kind of get you comfortable with this. Okay, now I'm going to show the second thing. So the next thing I'm going to do is I'm going to take a power series and integrate it to get a new series for the integral. So start this one exactly the same way. What we want to write down here is we have the original series is the series k equals 0 to infinity of c sub k x minus a to the k like that. Okay, now what we're going to do now is we're going to integrate. We're going to integrate both sides of this equation. Okay, and this is just the generic sort of a demonstration of the theorem. It's not a real technical proof, but it's a demonstration. So what we're going to do is we're going to integrate f of x, and then we're going to integrate this series, okay, which is kind of weird, but we can do that. We can integrate it term by term. We haven't seen that yet, I don't think. But you could go through and integrate the terms in that series like that. Okay, we'll do that with respect to x. Okay, so here's what I'm going to have. Now what I'm going to do first of all is we just have the integral of f of x. Our goal is to have a series for that integral by integrating each term in that series. Okay, so we're going to write down the terms in this series, and then we're going to integrate term by term and get a pattern. Okay, so if k is 0 in this particular problem, we already did this. If k is 0, what do you end up with? You end up with c of 0, right? Okay, and then what you have right here is that would be x minus a to the 0, so that's just 1. Okay, go now to k equals 1. And you guys, when I'm done with this problem, if you want to get your phone out and take a picture, you can. Because I didn't put this on T2L, and I told you, you don't have to have this in your notebook. I don't test over this, but I do want to show you this for future reference. Okay, so when I'm done with this problem, I'll display it, and if you want to take a quick picture, you can. I mainly wanted you just to kind of follow along with this as I'm doing this. So if k goes to 1, then you would have c of k. And then that would be x minus 1, or x minus a to the first, like that. Now, whoops, that needs to be c of 1 like that. Okay, so that's c of 1. Now go to the next term. The next term is what? c of 2, x minus a to the second. Once you get here, the pattern's simple. So now it's c of 3, x minus a to the third, and eventually we get, go on, and eventually we get c of k, x minus a to the k like that. And that whole thing is dx. So we have not seen this before, but you can integrate, since a series is a sum of terms, can't you just integrate each part? Absolutely, you already know that. You've been doing that through 2 semesters of calculus, right? Okay, so what we're going to end up having now is we're going to go ahead and we're going to integrate each term. And we're just going to do this in our head. So if you integrate c naught, that's just c naught k, right? The derivative of c naught k is c naught, so we're going backwards now. Okay, if you go to the next term, you're going to have c1 x minus a to the second all over 2. Okay, that's what that term's going to be. That's a power rule is what I'm applying. When you go to the next one, you're going to have c2 x minus a to the third over 3, like that. And then if you go to the next one, that would be c3 x minus a to the fourth over 4. And then, dot, 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 we would go out here. Now tell me what the last term is. If you integrate this last term, what would you get? C of k, that's a constant, right? Then what? X minus a to what power? What? K plus 1 all over what? K plus 1. What do you do at the end of an integral always if it's an indefinite integral? Plus c. There you go. Okay, so that's what it is. So if you look at this, what we kind of end up with is, see this last term right here is what's in that theorem, and that's the power rule. So what I'm doing is I'm doing a series expansion on that, and I end up getting that same formula. That's what this theorem says, is when you integrate a power series, you end up getting this. Okay, that's the general formula like that. So that's what I kind of want you to have down. Take a picture of that if you want to, for reference. I'm fine with that for what we're doing on this. Okay, now I am going to do a couple of examples just to kind of get you the idea going on this. Then we're going to go ahead and move on into just a real simple thing in 9.3 today also. Okay? All right, let's do just kind of one example on this next page. And I'm I think what I'm doing on this one is I'm giving you a power series. Yeah, I'm giving you this power series right here. This is a general power series that we've actually developed before. 1 over x can be represented by this infinite series x to the k, and it converges on the interval of -1 to 1 is what that is. So let's do this one together. This is probably a good one to write down and just do with me. Again, you don't have to have it in your notebook, but I'd like you to just kind of go through this with me. So what we're going to do is we're going to differentiate both sides of this equation like this. So I'm going to go through, and let's first of all, I'm going to go over to the side, and f of x is 1 minus x to the -1. I'm going to take the function. Everything I'm going to do in this problem is stuff that you can do, I think, with ease by now, really. So f prime of x, let's go ahead and do that derivative. So if we do that by chain rule, that's -1, 1 minus x to the -2. Derivative of what's inside is -1. So that's going to give 1 times 1 minus x to the -2. So that's 1 over 1 minus x squared. Okay, that's the first derivative of this function, correct? Okay, that should be a piece of cake for everybody. Okay, so what we're going to do on this is we're going to take this equation. This is a series I'm giving you, and what we're doing is we're going to develop a series for the derivative. Okay, so what we have is we just found the derivative of this piece is 1 over 1 minus x squared, like that. Okay, so we have, no, that's not how you write it. You write it like this. So you're going to write that as 1 over 1 minus x to the second, like that. Okay? Now what we're going to do is we're going to integrate all of the terms in this infinite series. So let's just write down that we're doing the integral of 1 plus x squared plus x to the third plus dot dot dot. Eventually we get out to the point where we have x to the k dx, like that. Okay? Now this will be something that'll be super easy to go through and do. Everybody with me okay so far? Okay? All right? So what I do with this, I'm going to bring this down. So I have 1 over 1 minus x squared. Now let's do this integral kind of together. So if you do the integral of 1, what's that? Of course, that's x. You do the integral of x, that's x to the second over 2. You do the integral of x to the second, that's x to the third over 3. And then you do the integral of x to the third, that's x to the fourth over 4. And you keep going out, and eventually, what's the integral of x to the k? X to what? K plus 1 over what? K plus 1. Okay, so we get all the way out like that. That's just applying a power rule like that. Okay, and then that will all be over k plus 1. Then you have a plus c like that. So see, what we have is we have a new series. And the idea with this thing is if you do this, then this becomes your new series like this. So you end up with this. Okay, you end up with 1 over 1 minus x squared. We got a new series that we can put together on that. And then this one just kind of goes like this. Now I'm going to put this together, kind of show you how I'm going to think through this just a little bit here. Is we're going to go ahead, if, let's see, if k is equal to 0, let's see, we end up having, let's see, am I doing the, oh, I'm doing the integral. Why am I doing the integral? You know what I'm doing? I'm doing part B on this problem. Okay, I don't know why in the world I'm not paying attention to what I'm doing on this problem. Okay, what I just did was I did the derivative, and for some reason I decided to integrate that. Okay, you guys didn't even notice, did you? Okay.
The derivative, why it's not negative?
What's that?
For the derivative, why we're not negative?
Well, because, let's see, when I did the derivative over here, what I have is I have -1, 1 minus x to the -2, but then the derivative of what's inside is -1, right? So then you have -1 times -1, so I got that right, but what I didn't do, and I don't know why I did this, I just kind of going through the motions, I think is what I was doing. So anyway, that's what the derivative is. My apology, that's what I need to do on part B, but I want to do this right, then I want to do one more specific example. Okay, so here's what we're going to do. What you're going to do now is you're going to differentiate the terms of this series. Okay, so what do we have? What's the derivative of 1? 0. What's the derivative of x? 1. derivative of x squared, 2x. Okay, then next one's going to be 3x the second. Okay, eventually you get up to a point where when you do the derivative of x to the k, that just gives k x to the k minus 1 like that. Okay, so that's your derivative like that. So see what this does is, that's a real simple thing to do. We did the derivative of 1 over 1 minus x squared, okay, or 1 over 1 minus x, and I did the derivative of each term in the series, okay? So what I want to do from here now is I want to write the terms on here, okay? So if I go through and do this now, I'm going to end up with this, okay? So this is basically, I'm going to write one more step and then put this together. So that's like 0 plus 1 is 1, so I really just have 1 plus 2x plus 3x the second, dot, 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 all the way up to the general term like that. Now what we're going to do is we're going to write an explicit formula for that series then. So when I do this, I'm just going to say this, okay, if k is equal to 0, we're going to start the series at k equals 0, we get 1. If k is equal to 1, we get that term. If k is equal to 2, we get that term and so forth. So we want to just see if we can write an explicit form for this then, okay? Well, first of all, here's what I see. If k is 0, 1 is 1 more. If k is 1, 2 is 1 more. If k is 2, the 3 is 1 more. So what you're going to do there is you're going to write an expression for that 1, 2, 3. What that's going to be is that's going to be k plus 1, right? Does everybody see that? Okay. All right, how about the power? Do the powers, are they the same or do they match? Hold on, that was a dumb question. Are they the same or do they match? Okay, that means they're the same. I meant to say, are they the same or different? Okay, see, basically on this, that's x to the 0. So you'd have x to the k power like that. So that's your general series like that. So what we have is I'm just writing an explicit formula on that. So what we have, you bring this down, and then this would be the conclusion we have. Okay, we have that. So here's what you come up with. So based on this power series that I gave you, we can conclude that we get a new series. We get 1 over 1 minus x squared is equal to the series k equals 0 to infinity of this thing. Okay, k plus 1 x to the k like that. All right, so that's what I'm doing. Is part of the benefit of this is if you know one series, if you know a power series and you know its result as a function, then if you differentiate it, you can get a new series. Okay, did that make sense what I did? That's not that hard of a thing to do. You can do that term by term, and then you can write your solution in a series like that. Okay, now I'm going to do the integral, and then I'm going to do probably just one other illustration of that, you know, out of the book to just give you a feel for this. Okay, so what I'm going to have here is we're going to go ahead and integrate now. So what we want to do on this is we have f of x like this, and what we have here is we were given that that's 1 over 1 minus x, okay, and then we were given that that is the series k equals 0 to infinity of x to the k like that. Okay, so that's what we have so far, and then we can write out those terms in the series. So what you're doing in this problem, the directions say integrate the series term by term, and then you're going to get a new function. Okay, that's what I started doing on the last one. Okay, so over at the side of the paper, let's work out this integral 1 over 1 minus x dx. With a little practice, you can do that in your head. What kind of integral does that look like to you? That's a natural logarithm, right? You got to be careful with the constant on that one. But it kind of looks like you would have ln of 1 minus x. Not quite, though, because if you did a derivative of 1 minus x, you would have 1 over 1 minus x times negative 1. Okay, so what you have is actually the value of this integral is negative ln of 1 minus x plus c. Okay, you could do that with u substitution, but you don't really have to. You can just reason out that you have that extra negative. Okay, is that clear? Okay, all right. Now what we're going to have is we're going to have this. we're going to go ahead and write this down as the integral of f of x. That's going to be equal to we just did the integral of 1 over 1 minus x. So let's write that down as negative ln 1 minus x. I'm not going to worry about the c. Okay, that's going to come into play at the end of the problem. So I just kind of bypass that for now. Then what we're going to do is we're going to do the integral of term by term, the terms in this series. Okay, so we're going to have that. Okay. All right. So let's see what we have going on here then. So I'm going to bring this down right here. What we're trying to do is we're trying to find a series representation for that expression negative ln of 1 minus x. That's what our goal is. So what we're going to do is we're going to integrate term by term this power series. So let's just write out the terms. If k is 0, you have x to the 0 or you have 1. If k is 1, you have x to the first. Then you have x to the second, x to the third, dot, dot, dot forever, x to the k times dx. Okay, so that's what we're going to do. All right, everybody with me so far? Okay. All right, now let's start integrating. Let's keep bringing this thing down. So this is ln 1 minus x. Now just do the integral. This is easy stuff to do in your head. What's the integral of 1? X. Integral of x to the first. X squared over 2, and so forth. Just do that real quick. X to the third over 3, x to the fourth over 4, dot, dot, dot. Eventually you get to x to the k plus 1 over k plus 1. And then you do have a plus c out at the end like that. Okay? So what I'm going to try to go through and do on this then is we're going to try to come up with a formula. Okay, we've got the series written out like that. And the idea is, let's see, if k is equal, this time I think I'm going to start, you can always start k equals 1 or 0. To me, it's just as easy on this one to start k equals 1. That way, that'll match up with that exponent. So if k is 1, that's x to the first. If k is 2, that matches that. And it also matches that, which is kind of cool. If k is 3, that matches that, and it matches that, right? So what we're going to do then is we're going to write the result. So the result is going to end up being this. We're going to have negative ln 1 minus x is equal to, now we're going to write a series formula for this then. So we're going to start with k equals 1. We're going to go to infinity. Okay, so tell me what you think the explicit formula would be on this. Just look at one term and what would it be in general? It'd be x to what power over what? Can you tell me that at least? X to the k over what? Over k, right? Okay, isn't the denominator, isn't it going to match k? It's just, hey, the denominator is going 1, 2, 3, 4, so it's following k. The exponent is also following k, so that's going to be x to the k over k like that. Okay? So that's what we get. That's your result right there. All right? So what we did, which I think is kind of cool, I don't know about you, but if I give you a series, then you can differentiate it to get a new series, and then you can integrate it to get another series. So that's where a lot of these series come from. Once we figure out one basic series, and we could integrate this again if we wanted to, and come up with another series. Okay, you could differentiate over and over again, you get tons of series formulas. That's the idea. Okay? All right, so let's see. Let's do one illustration of this, and then I'm going to jump in. I think I want to do just a couple things in 9.3 to do the term-by-term stuff. Okay? All right, so I think I'm going to go ahead and go to 9.3. I think that's probably good enough that I just get that in for today.